All right, guys, this is graphing rational functions with oblique asymptotes. And you'll remember on the board on Friday, we had all of our steps, and under horizontal asymptote, I said there's only one, and we look at the exponents. And so if we look at this function right here, the exponent on the numerator of this function is 2. And the exponent on the denominator is 1. That means your top is 2 and your bottom is 1. And when the exponent on top is bigger, what that means is there is no horizontal asymptote. And lest you worry that that means that we don't get to do any horizontal asymptote math, I have good news. No horizontal asymptote means that there is something cool called an oblique asymptote. Sometimes they're called slant asymptotes, but it's an oblique asymptote, and it's an asymptote that goes sort of diagonally across the paper. And you can see that on your notes page off on the right side, that this function, x squared minus x over x plus 1, has a sort of strange diagonal asymptote. So I'm going to show you how you find that oblique asymptote, and then we're going to graph a rational function below and from beginning to end, just so you can see the whole process with the oblique asymptote. But I'm going to show you how to find the oblique asymptote first. So you find oblique asymptotes using polynomial long division, which I know that you guys were really sad to leave behind last week. So good news, it's back. And what we do is we divide the top by the bottom, because this is a bigger polynomial than this. So when we divide, we're going to get another equation. So this is x plus 1, and we're going to put that into x squared minus x, and then we should also have a number here, right? There should be a constant at the end, so I'm going to say plus 0. And then what we do is we say, okay, what can I multiply by x that will give me x squared? And the answer is another x. So x times x is x squared, and x times 1 is a positive x. And when we subtract, and remember that at this point we subtract, and you have to change the signs on every term, we subtract and subtract, you get negative 2x plus 0. And we bring that 0 down right there. And I say, okay, what times x will give me negative 2x? And the answer is negative 2. So negative 2 times x is negative 2x. And negative 2 times 1 is negative 2. And remember that we're going to subtract at this point, and that means that I change the signs of both of the terms there. And so I get 2, and that's our remainder. And that actually doesn't matter for us now. What matters is the quotient up here, the solution that we get. That is our oblique asymptote. And so our oblique asymptote is y equals x minus 2. And if you look over here on your notes page, you'll see that that's what they tell us. The slant asymptote is y equals x minus 2. That's where they got that. They did long division. They divided the top of the rational function by the bottom, and that quotient was your oblique asymptote. All right, so let's look at a rational function. We're going to do it beginning to end and see how that looks. So if I'm looking down here at this example, it says a rational function with a slant asymptote. The first thing I want to do is factor everything completely. And so when I look at this, I ask, can x squared minus x minus 1 be factored? And the answer is it can't. That is not a factorable polynomial. And so we can't factor the top of it, which means it can't be simplified. And that means there are no holes. And if there are no holes, like we can't factor, so there's no simplifying, we go ahead and write whole and then write none. And what we're doing is we're acknowledging that we looked for a hole and there wasn't one. So we want to go ahead and note that we looked for a hole but there wasn't one. And then we can move straight on to the vertical asymptote. And remember, you find that by setting the bottom equal to 0. So that's x minus 1 is equal to 0. And so your vertical asymptote is at x equals 1. That's our vertical asymptote. The next thing we want to find is our horizontal asymptote. And so we look at the exponent on the top, and in this case that's a x squared right there, and the exponent on the bottom, which is a 1, and the top is bigger. And that means that there is no horizontal asymptote. Let me zoom out here a little bit. There is no horizontal asymptote. And we need to note that. We need to say, hey, there's not a horizontal asymptote, so that I know that you looked for one and didn't find one. Now, if there is no horizontal asymptote, there must be an oblique or slant asymptote. So we're looking for oblique asymptote. And we look for that by doing division. So we say, okay, x squared minus x minus 1 divided by x minus 1. Like that. And I say, what times x will give me x squared? And the answer is x. So x times x is x squared. X times negative 1 is negative x. And remember that when we do this subtraction, we change the signs on both of our product down here, the thing we got by multiplying. And what we get is 0 and minus 1, which is just negative 1. Can I multiply x by anything that will give me negative 1? And the answer is no, I can't. So this negative 1 is our remainder. And that doesn't really matter to us anymore. What matters is this number up at the top. And that is my oblique asymptote, is y equals x. That's my oblique asymptote. And when we go to graph this, we're going to draw a line y equals x diagonally across the graph. Now, that's oblique asymptote. We are almost done. Now we need to find our intercepts, and then we'll put it all together on the graph. So x-intercept, I set the top equal to 0. This is x squared minus x minus 1 is equal to 0. And I solve for x. And to do that, we might need to use the quadratic formula here, guys. So we're going to try that. This is x equals negative of negative 1 plus or minus the square root of negative 1 squared minus 4 times 1 times negative 1 all over 2 times 1. This is 1 plus or minus the square root of 1 plus 4 over 2. And that is x equals 1 plus or minus the square root of 5 over 2. And this is one of those places where you do actually want to pick up the calculator and calculate those numbers because we are graphing, or not, yeah, because we're graphing, so we need to know those actual numbers. This is 1 plus the square root of 5 divided by 2, and 1 minus the square root of 5 divided by 2. And we're going to find the numeric answers for both of those. So 1 plus root 5 is 1.618, and 1 minus root 5 is negative 0.618. And so those are my x-intercepts. And we want to write those as points. So this is 1.618, comma 0, and negative 0.618, comma 0, like that. Those are my x-intercepts. And then y-intercepts, guys, we find the y-intercept by putting in 0 for all the x's and solving for y. So y equals 0 squared minus 0 minus 1 over 0 minus 1. It's y equals negative 1 over negative 1, which is positive 1. So our y-intercept is at 0, 1. And what we do is we take all of this information, my vertical asymptote, my oblique asymptote, my x-intercepts, and my y-intercept, and I put it together on this graph. So I'm going to graph both of my asymptotes in red just so that they're easy to see. I have a vertical asymptote at x equals 1. And this horizontal asymptote, it's the line y equals x. So that's a line with a y-intercept at 0 and a slope of 1. Right? You graph that like you would graph any line, except you make it dashed because it's an asymptote. And your graph is going to sort of follow those lines, which you saw in the example above, and I'll show you here as well. All right, my x-intercepts are at 1.618, so that's like here, and at negative 0.618, so that's about there. And my y-intercept is at 0, 1. And what this tells me is that I've got a curve that sort of follows this red line, goes through, there we go, through those 2 points and goes up towards that vertical asymptote. And then over here, I have a curve that sort of follows that vertical asymptote and then curves up and goes towards the oblique asymptote. So this looks sort of like a long curved X. And that's what those graphs look like. And this is why rational function graphs are just the coolest, is because you can start with something that looks like total chaos and get something that looks just awesome, like this. And because depending on what the equation looks like, you can have something that looks like this, sort of a wide diagonal X, or with the same sort of asymptotes, have something that looks like this, where see these curves are inside those asymptotes and these curves are outside those asymptotes like that. So yeah, it's just very, very interesting. All right, guys, that is oblique asymptotes. Get working on your assignment. I have also posted a picture of the steps from Friday in the classroom. So remember that you want to have those steps with you every time you do one of these problems. And you want to make sure you're following those steps, one at a time, every time you do one of these problems.